So welcome everybody, my name is Carlo Maragliano and I am a graduate student in Masdar Institute in Abu Dhabi. Today with this presentation I will present and introduce my research proposal for my PhD thesis. The title of the thesis is Spectral Beam Splitting System for Efficient Conversion of Solar Energy, Design, Simulation and Characterization of System Components. So here is the outline of my presentation. First, I will present the research objective of the PhD thesis. Second, I will focus on two parts. The first part will be dedicated on analyzing the spectral beam splitting solar system. I will propose the motivation for this work and I go through a quick literature review. Finally, I will present the results and the future work. In the second part, I will focus on the characterization at the micro and nanoscale of nanostructured material for solar energy harvesting. I will propose the motivation for this work and go through a quick literature review. And finally, to conclude the presentation, I will go through the results of this second part. So here is the graphical summary of the research proposal. Basically, this is divided, it will be divided in two parts. The first part will be about developing a spectral beam, spectral splitting concentrator based system for the efficient conversion of solar energy. Basically, this system is composed of two parts: an optical element that is able to spatially separate different wavelength bands and to concentrate the light at the same time. And the second part will be composed of solar cell made of different material, each one matched with the wavelength band that is shine on top of it. And the second part of the research will be dedicated on developing and analyzing different techniques for the characterization of solar cell, particularly the electrical and thermal properties of solar cell with micro and nano resolution. This work will be divided in different steps. The first part will be designing the system, the second simulating the system, combining optical and electrical simulation, and finally I will focus on the manufacturing part and the characterization of the overall system. So everybody knows that solar photovoltaics is one of the most promising solutions for sustainable energy production. However, there are still some key issues that need to be unlocked to actually obtain the maximum from this technology. And in order to push the limit of such a technology, it is important to understand the principle of operation of solar cells. So here we will focus on how different photons are absorbed by solar cell. So maybe solar cells are made of semiconducting material, and this semiconducting material are characterized by a band gap, which is basically a region of energy within the lattice and the material in which the electrons inside the material are not allowed. So here is the equation of the energy of a photon that can be written as the multiplication between the Planck constant and the ratio between the light velocity and the wavelength. So in case the energy of the photon is higher with respect to the energy of the band gap, we actually have absorption of the photon and the generation of electrical carriers inside the semiconducting material. In the case in which instead the energy of the photon is lower with respect to the energy of the band gap, we don't have any generation of carriers inside the material, so we don't have any absorption. In order to be coherent with the definition of the energy for the photons, I define here lambda cutoff, which is basically property of the material, and we'll see later how this is important in order to understand how the solar cell absorbs the energy coming from the sun. So the picture now is not complete yet, because we have to look at how is the source, how is the energy and the distribution of energy of the photons coming from the sun. This can be seen by looking at the solar spectrum, which has a very wide and broad range that goes from circa 400 nanometers to 2500 nanometers. So let's look now how a single junction, homojunction solar cell absorb the energy coming from the sun. So we define here a cutoff wavelength for this material. Remember, the solar cell in this case is made of one single material. So what happens if we take a wavelength, a photon that has a wavelength higher with respect to the cutoff? Well, in this case, the energy of the photon is not enough to generate, to be absorbed, so we don't have any generation of electrical carriers inside the material. In case the wavelength is slightly below the cutoff wavelength, the wavelength of the photon is slightly below with respect to the wavelength of the cutoff wavelength, we have a very efficient generation of carriers. This is because this difference in energy between the photon and the bandgap of the material is very small. What happens instead if we have a wavelength, a photon with a wavelength that is way below the cutoff wavelength? Well, in this case, we still have generation of electrical carriers inside the material, but the extra energy that is carried by the photon is lost to a process called thermalization, which is basically consists in generating heat inside the material. So we see that there is a spectral mismatch between the solar spectrum and the spectral response of a single junction solar cell. One technical solution that has been proposed in literature to compensate for this difference consists in stacking different material on top of each other in order to create a so-called and to design a so-called multi-junction solar cell. The idea is to design such a solar cell in the way that the top layer is made of a high bandgap material, while the bottom layer is made of a low bandgap material. So how does it work? Well, in this case, we have three, or in general, n material. And in the specific case here, we have three material. And so we have three cutoff wavelengths. So what happens if I want to absorb these three different colors, the blue, the green, and the red one? Well, in this case, we have a very efficient generation because if you look at the top layer, so the layer to the left in the diagram band, the blue photon is absorbed while the green and the red one are transmitted through the first layer. The green photon is absorbed in the second layer, while the red one is transmitted through the second layer, and finally arrives in the second layer in which it is absorbed. So we understand in this case, compared to the previous case, that we have a very good and efficient generation of electrical carriers. And such a technical solution allows to boost the efficiency of solar cell up to a theoretical maximum of 68%. However, there are some limitations, some challenges related with the manufacturability of this solar cell. In particular, we have some limitation in terms of which material we can use for multi-junction solar cell. Indeed, when we stack two materials on top of each other, and these two materials have different lattice constant, we have the generation of so-called misfit dislocation. And these misfit dislocation are very detrimental for the efficiency of solar cell because they act as a recombination center. Here in this graph to the bottom left, we have I categorize the different material based on their bandgap and lattice constant, and here I've underlined the region in which we have the material that are mostly used for multi-junction solar cell. There are gallium indium phosphide, gallium arsenide, and germanium. So here it's pretty clear that we are limited by, in terms of which material we can use for multi-junction solar cell. Consider this limitation at the end of the 60s and 70s, at the beginning of the 70s, another technical solution has been proposed to compensate for the difference between the solar spectrum and the spectral response of solar cell. This solution consists in using an optical element that is able to spatially separate different wavelength bands of the solar spectrum. These spatially separated wavelength bands then are directed towards different solar cells so that each wavelength band can be efficiently converted into electricity. So the concept here is explained again. Basically, the idea is to separate in space different region of the solar spectrum and to direct each of them to the most efficient, to the most proper solar cell. So with respect to the Venn diagram that we have seen before, the scenarios were pretty much similar, but we don't have multiple transmission through the different solar cell. Why we don't have multiple transmission? Because the configuration for spectral splitting, the solar cell, as we can see to the right, are put in tandem on the same ground. So they are not stuck on top of each other as we have seen for multi-junction solar cell, as we can see in the picture to the left. So for solar cell designed for spectral splitting system, we don't have any limitation in terms of material that we can use, because material are not stuck on top of each other, so we don't have the generational misfit dislocation. So we can use any kind of material and we can grow them as we prefer. So we can use thin film material, polycrystal, or amorphous material. So in this sense, we are pretty much limited. So spectral splitting is generally used with concentrated light. And going through the literature review and reviewing the different spectral splitting concentrating solar systems that have been proposed in literature, I have identified two macro categories. The first category is called discrete component design, in which basically the concentrator and the splitting element are two different elements. So the concentrator that is generally a lens and the spectral splitting element. While the other category is called integrated component design, in which basically the splitting element and the concentrating element are combined in one single optical element. So let's go through a review of the discrete component design that are being proposed in literature. And in this first part, I will focus on the splitting element. So for what regards the splitting element, literature has been used different solution. As optical filter, we can use the electric thin film filter, which can be made of a sequence of periodic layers with different refractive index. Or as an alternative solution, we can use a Rougate filter that is basically a layer with a continuously varying refractive index structure. The other solution that has been recently proposed, coming from MIT, consists in using a broadband diffraction optical element that basically uses the diffraction to spatially separate different wavelength bands, so different color of the solar spectrum. While another solution, which is basically very easy and intelligent, consists in using spectrally sensitive mirrors to direct different wavelength bands of the solar spectrum towards solar cell made of different band gaps. All these concepts, all these ideas can be combined in such a system that has been proposed by Gottsberg it's basically a light trapping scheme that can allow to reach very high efficiency. So these elements, spectral splitting element, are put on top of each solar, can be put on top of each solar cell in order to reach very high efficiencies. Well, another solution, as we said before, so the second macro category of spectral splitting system consists in integrated component design, in which we don't have a separation between the concentrator and the splitting element, but these two are combined together. Obviously, in this case, we have a great advantage because we can actually reduce the optical losses that are due to repetitive and multiple reflection at the different interfaces. So one solution that has been proposed in literature consists in using these shaped reflector that are made of two layers that can reflect different wavelength bands of the solar spectrum. So basically, each mirror, the dish-shaped reflector, is able to reflect one wavelength band of the solar spectrum and to direct it towards one focal point, and these two focal points of the two reflectors have an offset of 20 centimeters, so we can put two different solar cells made of different semiconducting material. Another solution that is being proposed in Masdar consists in using a set of solid transparent prisms that operate each of them independently. However, the superposition of each prism contribution results in the focal plane in concentrated and at the same time spectrally divided beams. So let's focus on this solution. And in order to understand how it works, let's focus on the behavior of one single prism. So, as we know, dispersive prisms are used to separate different colors of the solar spectrum. And this is the equation that here is reported to determine what is the angle of the exit angle of the light in relation to the wavelength of the light, and we have basically two important parameters here, which are the angle I1, that is basically the entrance angle, and the aperture angle A, which is the aperture angle of the prism. So we can define to have a reference angle, which is basically the angle that we obtain, the exit angle that we obtain for the lower wavelength of the spectrum. In this case, we took as a reference the a blue wavelength, and by combining different prisms in a curve shaped, we can obtain what we look for. So we can obtain a separation of different colors and at the same time a concentration of the light. And this is the optical element that has been designed. This has been realized by mechanical machining with an organic material. And these are the results. The results is we can see that the system actually works as we expected. It is able to separate different colors of the solar spectrum and to concentrate it in one direction. The limitation of this system is that this system is able to spatially separate different color and different wavelength but it concentrates just in one direction. And we know that solar cells for concentration have generally a dimension of 1 by 1 centimeter. So what we are looking for is a system, an optical system that is able to spatially separate the solar spectrum, the different wavelength band, but at the same time is also able to concentrate the light in two directions. So we would like to obtain something like this that is reported to the right side of the slide. So in order to achieve this, we have to change the element that composes our spectral splitter. The idea is to move from a simple prism to a trapezoid. And basically the idea is to introduce a new angle, which is the angle that we call here U, that allows us to concentrate also in the other direction. So here is a screenshot of the CAD file of the spectral splitter that we designed in Masdar, and here we can see magnification of this screenshot, in which we can observe the trapezoidal shape of each element. And this is how the whole system looks. So the distance between the optical element and the focal plane is 32 centimeters. And we took, as I mentioned before, as a reference blue color, so the wavelength of blue, and we have a separation in this sense between the position of the optical element and the focal plane along the y-axis of the blue color that is of 20 centimeter. And in order to make sure that our design was working fine, we decided to implement the design on ray tracing software called Trace Pro. And by doing so, we were able to determine the optical performance of the system. And what we see on the top right picture is a separation, is the result of the simulation that we obtained with Trace Pro on the focal plane. And as we can see, we use 3 different colors, and we can see a very good separation of these colors, a separation of circa 3 centimeter between the red and the blue wavelength. And we obtain also a very good concentration in both directions. And the overall performance of this optical element are here reported. We have an average transmissivity of 76% and a maximal geometrical concentration of 210x. And the beauty of this system is that we are free to choose the material that we like the most. So we were not limited in terms of which material you can use for the solar cells. And so we can use, for example, in order to cover the whole spectrum, we can use germanium, silicon, and gallium arsenide, or we can use either other material, like for example, germanium, CIGS, and CGS. So we can use the same material, but simply by changing the concentration of one element, we know that we can change the band gap. So we are pretty much like free in the choice of the material. But obviously, simply by looking at the optical simulation, we don't have the whole picture of what are the potential of such a system. So we decided to combine the optical simulation with the electrical simulation of the solar cell realized with TCAD, and this is the set of material that we use: germanium, silicon, and gallium arsenide. And we obtain in this case an overall efficiency of 28% without any current optimization, and we determine also an efficiency of 40%, maximum efficiency of 40% in case we have a current matching between the different solar cells. So the simulation confirmed the very good potential of such a system. So here is finally our optical device finally realized. The optical device has been realized by injection molding. It has a dimension, as we can see in the picture in the bottom, of 3 cm times 7 cm, and here are reported preliminary results. We can see that our optical system is actually able to separate different color of the solar spectrum, as reported also in the spectrum to the right. However, we still have to confirm if it is able actually to concentrate the light up to the efficiency that we determined by the simulation. So the next step and the future work will be to complete the characterization of the optical device and to determine if there are discrepancies between what we obtain experimentally and what we determine with the simulation, and finally to combine the device with a set of solar cells to verify experimentally the result of the simulation that we have seen before. So let's move now to the second part of the research. We know that in order to characterize solar cells, nowadays it's important to have techniques that are actually able to quantify electrical properties with a high spatial resolution. Why this? Well, because today in solar cell we use like nanostructure, like nanoparticles or nanowires in order to enhance the electrical and optical properties of solar cell. Therefore, there's the need to quantify electrical properties of the solar cell with a high spatial resolution. And in particular, I will focus on determining the electric constant and the charge carrier concentration, which are two parameters that are crucial and very important in order to tune and optimize the properties of solar cells. For this purpose, I will use an atomic force microscope. Atomic force microscope is a microscope that, with a cantilever, allows to determine. We have a cantilever that is shaped, and by looking at the dynamic parameters like amplitude, frequency, phase, and deflection, we can reconstruct the topography. But this tool is very versatile, so I will show in the next slide how we can use it to determine electrical properties of materials. So in this part, I will develop different techniques to determine and quantify the electric constant and charge carrier concentration, and I will develop the analytical framework, and in the second step I will implement this analytical framework by doing some measurement, and I verify the results by comparing the results with measurement done with other techniques. So in literature, two different techniques are used to determine the dielectric constant with the atomic force microscope. One is called scanning capacitance microscopy, and the second one is called alternating current electrostatic force microscopy. In the first one, the current that flows through the tip while it's shaped on top of the sample, of a bias sample, is measured by changing the equilibrium distance between the tip and the sample. A current versus distance curve can be reconstructed. While in alternating current electrostatic force microscopy, the tip is actually shaped with an voltage, an AC voltage, and the dynamic of the cantilever is observed in order to determine the capacitance versus distance curve between the tip and the sample. And in literature, we can see that both techniques have been used to determine the dielectric constant of the material simply by comparing experimental curve of the capacitance between the tip and the sample with an analytical method. And both techniques have been successfully used to determine the dielectric constant. However, they have some limitation. For example, SCM has a limitation because there's a need of an external current amplifier in order to measure the current that generally is not implemented inside the microscope. While for the second one, there are some limitations in terms of which are the parameters that we can use in order to reconstruct the experimental curve in order to analyze the result. And there are some limitations in terms of the oscillation of the tip and the tip sample distance. For this purpose, in order to quantify and to analyze this limitation, I have developed a simple model that shows that the approximation used in order to obtain experimental result with the AC-FM technique holds for very small oscillation amplitude, and then the technique also suffers from sensitivity limitation at large tip sample distances. So we have limitation coming from both techniques. So what I decided is to develop an alternative technique. So the idea is to reconstruct the nonlinear tip sample conservative force curve, and to do so I have used a formalism that has been proposed in literature by Dr. Seder and Dr. Katan that allows to reconstruct the force curve between the tip and a sample by looking at two experimental parameters, which are the amplitude and the phase. This technique consists in three different steps. The first consists in measuring the effective work function by fitting force distance curve with an analytical mode, with an analytical model. The second step consists in recovering force distance curves that are solely affected by conservative short-range interaction, and this is done by applying to the tip a voltage that is exactly the same as the work function difference between the tip and the sample. In this case, we can compensate for the electrostatic force between the two, so we reconstruct just the so-called short-range forces, so Van der Waals forces. And the third step consists in subtracting the previous curve from the general curve, so in order to reconstruct a force that is solely affected by electrostatic interaction, and finally from the force we can derive the tip sample capacitance curve. And I have shown also that this technique does not have the same limitation as the ACFM technique, because even if we change parameters like the amplitude or oscillation of the cantilever, we obtain always the same force. And in order to confirm the validity of this technique, I have compared the experimental result that obtained with this technique with an analytical model in order to determine the dielectric constant of a thin film of zinc oxide film, and obtaining a very good matching with measurements that are being reported in literature and results obtained with macroscopic techniques. Another, as we've seen before, another important properties for solar cell is the charge carrying concentration. Charge carrying concentration are very important in order to optimize the quantification of this property. It's very important in order to optimize the properties of the performance of solar cell. And in particular, this is especially important for zinc oxide that is used as a transparent conductive oxide on top as a top layer of solar cell. And we know that the zinc oxide is a particular material. Indeed, it's not doped with external element like boron or phosphorus in silicon, but this material is generally intrinsically doped with zinc interstitial of oxygen vacancies and hydrogen. So the determination of the charge carrier concentration in this material is generally trivial. So what I've done, I've developed a technique that uses atomic force microscope to map the charge carrier concentration in zinc oxide thin films. To do so, I've used an operational mode that is called scanning cavity probe microscope that basically determines and is able to map the work function difference between the tip and the sample. And I've developed for this an analytical framework in order to move from a map of work function difference to a map of charge carrier concentration. And I have verified the results of, this framework has been implemented in a MATLAB program, and by doing so I was able to obtain map of charge carrier concentration. And the results obtained with this technique have been compared with other technique, obtaining a very good matching. So finally, I will focus on another aspect and another properties that is very important to determine in solar cell, which is their thermal properties. We know that especially in solar cell for concentrated light, these are exposed to very high light intensity, and therefore it's important to determine their thermal properties with a good spatial resolution, and also to determine how the heat is transmitted through different layers. We know that indeed that solar cell for concentrated for concentrated light have dimension in the order of 1 centimeter by 1 centimeter. So it's actually good to have a technique that is able to map thermal properties with a high spatial resolution. So to do so, I used, in collaboration with Boston University, a pump and probe system that is used to determine thermal properties of thin film layers. This system is composed of two lasers: the pump that is used to locally heat the sample, and the probe that is used to look at the change of reflectivity of the top layer, which is generally a metal. And the change in reflectivity is for small changes of temperature proportional to the change in temperature. So by doing this, it is possible to determine the temperature of the top layer. If we have a system that is composed by different layers, it is important to determine how this the heat propagates. And in order to do so, what we can do is to compare the experimental result with an analytical model. So in particular, we use a technique that is called frequency domain thermoreflectance. In frequency domain thermoreflectance, the power and the intensity of the pump is sinusoidally modulated, and what we look at, so what we measure, is the phase difference between what is measured with the probe and what is used to modulate the pump. So this measurement can be done at different frequencies, as can be seen in this graph, from frequencies in the order of 10 to the 5, from frequency to the order of 10 to the 7 Hertz. And as I was mentioning before, by using an analytical model that has been proposed by Dr. Cahill and then adapted by Dr. Smith in Dr. Matteo Chiesa for frequency domain thermoreflectance, we can, by comparing experimental results with this analytical model, determine the thermal properties of the different layer our sample is made of. So here to the right we have the setup of the system. The frequency domain thermoreflectance was used before as a technique to locally measure the sample, and our idea was to extend it to a mapping technique, so to a microscopy technique that is able to map thermal properties in 2 dimensions. So in order to do so, we decided to put the sample on a piezo stage and to modulate at the same time the pump with 6 different frequencies in order to make the acquisition of the data faster, and to determine finally at the same time simultaneously different properties of the sample, like interface conductance, thermal conductivity, and heat capacity of the different layer of the sample. And here is the result that we obtain on a sample made of silicon encoded with gold and titanium. So we compare the experimental result with the sensitivity of the system given by analyzing the analytical model that I was talking about before, and by doing so we were able to reconstruct map of thermal properties. In this case, to the left we have interface conductance, and to the right thermal conductivity, and we obtain very good matching, with result of measurement reported in literature and obtained with the other techniques. So we decided to actually explore the limitations of such a technique by applying the same technique on very thin layers. So for this purpose we use graphene, and the idea was to determine the thermal properties of graphene depending on the layer. In addition to that, we wanted to determine how the thermal properties of graphene change when we coat graphene with a metal. So we prepared different flakes by mechanical exfoliation so that we could have at the same time a region of graphene made of different layers. And we applied the technique in order to determine the thermal properties of graphene, in particular the interface conductance between graphene, between the metal layer on top, graphene, and the substrate underneath, which was silicon dioxide. And that's what we obtained. To the left, we can see the maps, and to the right, we reported two graphs in which we analyzed the thermal boundary conductance, which is basically the interface conductance, and the thermal conductivity. And we obtained results that are very good matching with the results, other results reported in literature, and in particular, we obtained the highest thermal conductivity for a single layer metallized graphene. So with this, I will conclude the presentation, and I would like to thank you for listening.